All right, let's look at sample test 5. Number 1, what is the closest apparent depth of a coin 5 meters below the surface of a pool? Use n equals 1.33 for water. So we have water, we have a coin that's 5 meters underneath, but it's going to, the light is going to bend as it comes out, and so it'll look like it's got a different depth. So we called this big depth D, something like that. So the apparent depth, little d, was big D over N2, the index of refraction for the liquid or whatever the thing is inside of, and so let's call it, that's water, so that's 1.33, so we got 5 over 1.33, so we'll get 3, so the apparent depth is 3.76 meters, and so which one is closest? Just a little bit closer to C, 4 meters. All right, the wavelength of light that travels through a material depends on the light's color. Yes, the wavelength changes as we go through a material or into a different index of refraction, so we would say true, A. If the magnification of a lens is negative 5.9, you know that, so m equals negative 5.9. We have the rules that if the magnitude of m is greater than 1, then it's larger, right? If it's less than 1, then it's smaller. And if m itself is positive, then we know it's upright. If it's negative, then we know it's inverted. So this one is larger and inverted. All right. Image is not upright, no. Closer to the lens, DI is smaller than DO, no. Larger, yes. Okay, so it's just the only one that works here is larger, so that would be C. A ray of light strikes a diamond from the air. What is the phase shift of the reflected light wave? All right, so we talked about we have two substances, N1 and N2. If N2 is bigger than N1, then we get, when the light comes in, it gets a 180-degree phase shift or a pi phase shift, right? So basically, this is where a ray starting in N1 and bouncing off of something with N2. So there is a pi phase shift. And so if it was going up, well, anyway, the wave has a shift of pi, so that's A. All right, a ray of light inside film strikes air. What is the phase shift of the reflected light? So we have some, like a thin film, maybe like an air, like a bubble or something, where we have air, and then we have some sort of other substance, maybe water or soap combination, and then it's back to air inside the bubble. And so it says inside strikes the air inside the film. So we're talking about this ray of light inside the film. It's hitting that boundary and bouncing off, and then it's going to refract again when it comes out here. But we're asking about in here, is there a phase shift between this ray going in and then when it comes back out? And so in this case, we've got N1 is equal to air, and this one is inside of the film. It's going to be bigger than air, say it's soap or something. N2 is going to be bigger than N1, but now we're starting in N2 and going to N1. And so when we're going from, when we have a phase shift, or we have a reflection from something that has a higher end to a lower end, then there is no phase shift. So this one would be 0. All right, when the reflection of an object is seen in a plane mirror, the image is, so we it's kind of, I guess we started with this, but so it looks like it's behind the mirror. Just draw an arrow, I guess. And it's upright, the same size. Let's see. So it's behind the mirror, so it's on the dark side. And so it's virtual, so it's one of these. And it is upright. When we look in mirrors, we don't see ourselves upside down, so that's B. The image formed on the retina of the human eye is always, and so we have something in here, we have a converging lens, we always get an image that's back inside the eye, it's upside down, and it's on the side of the lens where the light travels after it hits the lens, so it's real. So it's inverted and real and smaller. There we go. So that's a D. Alright, when doing the double slit experiment, we see a collection of small dots separated into larger blobs, light patterns centered around the zero location. What determines the width of the larger blob? So this is talking about like what we saw in lab. We had something like this, and then we had a group over here and a group over here, and then another smaller group kind of thing. And so we're asking what determines the width, this width. Alright, so remember when we did the single slit, we saw the same kind of thing except for it was solid bands. Alright, and so it can't be that it's the slit separation because we saw the same thing for just one slit, so it must be the slit width. Anyway, if you forget, you can think of it that way to remember. So it is the slit width that causes these causes or determines how far apart or how wide the bright is or how far apart the darks are, which is basically the same thing. Okay, which is the closest to the resolvable angular separation for 500 nanometer light through an aperture 1 millimeter wide? Closest resolvable angular separation. So we had, for a circular aperture, we had that sine theta is 1.22 lambda over d. And so if we want to, remember Raleigh's criterion said that the peak of one, the second one needs to be at least far enough over to be in the valley of the second one, so at that angle where the minimum occurs. And so this equation is for the first minima, and so we want the next one to be that far over. So the angular separation needs to be that. So, and I think you probably have this equation on your equation sheet for the critical angle, or the I guess it was resolvable angle, inverse sine of 1.22 lambda over d. Lambda is 5, so we want inverse sine. So inverse sine of 1.22 lambda is 500 nano, 10 to the negative 9. And divided by d 1 millimeter. 1 times 10 to the negative 3 meters. Alright, so inverse sine 1.22 times 500 negative 9 divided by 1e negative 3. So we get 0.035 degrees. So the closest one would be this one, A. Alright, sorry. Okay, number 10. We look through two lenses at once, one with magnification -5, one with magnification of negative 5, and one with 0.5. What do you see? Well, let's get the total magnification first. So that's going to be the two multiplied times each other, m1 times m2, so that's -5 times 0.5, so the total magnification is -2.5. So again, like we saw before, if the magnitude is, so the magnitude of m total is greater than 1, so that means it's larger. The combined image is, the image through both of them will be larger than the original object, and then since m total is negative, that means it will be inverted. So it should be larger and inverted, excuse me. So inverted and larger than the object. There we go. A. In Young's double slit experiment, both the distance of the screen and the slit separation are decreased by 50%. What happens to the distance between the same two adjacent bright fringes? Alright, so we've got the equation y, let's call it y sub m in general, is L m lambda over d for bright fringes for the double slit. Yes. Okay? And so, or at least approximately. And so we're saying that distance to the screen, that's L, becomes half of what it was. So we get L over 2 m lambda, and the slit separation d also becomes half of what it was, d over 2. So we see that this is our new ym prime, whatever. And we see that the 1/2s will cancel out, so we get ym prime is just the same as ym, so there's no change, stays the same. Okay. Right. If the wave from one slit of Young's double slit setup arrives at a point on the screen 1 full wavelength behind from the other, what is observed? So this is, we have one here, and then the other one is like this, but then it's 1 full wavelength behind, so they are, should be peaking at the same time, valleying at the same time. So we see this is what we call constructive interference. Totally constructive because they're exactly lined up. Total constructive interference. And so we should see double the brightness, or anyway, a bright spot. All right, the brightest kind of combination that we have. So it would be bright fringe. That would be. Okay. Excuse me. Which color would a thin film of thickness 240 nanometers and n equals 1 before not reflect is what that probably should say, not reflect. Okay, so we're looking for now destructive interference because we're getting not reflected. And it's a thin film, so we have a thickness, T is the thickness, and we have an equation for this. And so this is, we'll assume it's a thin film in air, and so the N of the film is higher than the N of the surrounding material. So we can use our equation for destructive interference. Yep, destructive interference for a thin film. And so that equation is M, some total number, some count, we'll probably want to take the minimum to be just 1, equals 2 times the thickness times N of the material divided by the wavelength of the original light. Yes, we have wavelength. Okay, and so we're going to just assume it's the thinnest film, so we're going to just take this M. Remember, the M is kind of like a counting integer. We'll take the skinniest one, the first M. And so then lambda, or what are we looking for? Thickness. So let's solve this for T. So T is going to be lambda over 2N. Yes, so we would have 240 nanometers over 2 times 1.4. 240 nano divided by 2 times 1.4. It's like 85.7. 10 to negative 9 meters. So 85.7 nanometers is our T. It's at least the thinnest T. Whoops, what am I doing here? What color? Okay, sorry. Not reading the problem very well. What color? So that's asking, basically asking us lambda, and we're given the thickness. Okay, we're given T equals 240 nanometers. All right, try this again. So we want lambda, and so let's solve this for lambda. That's even easier. So lambda equals 2Tn. So 2 times T, which is a 240, 10 to the negative 9, times N, which is the 1.4. And so let's do that. Times 1.4. 673 nanometers for lambda. All right, and so our new handy dandy equation sheet has our spectrum on it. So 673. So here's 600, here's 700, 673 looks pretty much red. Red. Okay. How thick, so now it's asking for T, should a non-reflective coating with N equal 1.4 be on top of glass with N equal 1.5 to block red? So this red now we're taking is 670 nanometers. Mark the closest answer. Alright, so again we're doing blocking red. So blocking means destructive interference, right? Our thin film, or a thin coating on thing has a different equation, right? Because the reflections they both when it hits the film from the air, there's a pi reflection or pi phase shift, and then when it hits the film from the film to the glass, there's another pi reflection because N equals 1, and then N equals 1.4, and then N equals 1.5. So both of them will have a pi in it. So it's kind of the opposite. Even though they're both destructive interference, this one's going to have the half wavelength kind of number in there to get the destructive interference. And so our equation for this is 2T is equal to M plus a half times lambda over N, right? The wavelength inside the film. And so, lambda over N is lambda sub N, which is the wavelength inside the film. So this is the wavelength of the of the light in the air to start with. And so we want T, let's see, we'll take M to be the smallest. In this case, the smallest M is 0. And so we can say T is going to be divided by 2, so it's going to be lambda over, got a half and a divide by 2, so lambda over 4n. And so lambda is 670 10 to negative 9 is 4n 1.4. Okay, 670 nano divided by 4 times 1.4. Looks like 120 nanometers for the thickness. So that is closest to 120 nanometers. I'll go see. All right. Which of these are the correct ray diagrams for a converging lens? All right, so we're going to look at rays. The rays, one thing to check is if there's a parallel ray on one side, it better be converging to the focal point on the other, and vice versa. So this one looks good, and we've got one going through the center. So that looks like a good diagram. A is good. This one, look at this, it comes parallel and it goes off away from center, so that's a diverging, so that's not good. It's supposed to be converging lens. This one has got the converging shape parallel towards the center, but this one has diverging shape following it backwards, parallel, and then it goes off, so this one's not converging. Just not a good diagram. Some converging, some diverging, there's problems there. This one, we have parallel to focal. That's a converging pattern, parallel on this side towards the focal point here. This one is focal parallel, but if we follow it backwards, parallel, and then it comes down in, so it's got the converging pattern through the center, so that one looks good. Let's see, this one is parallel focal. This one goes through the center, but this one like goes straight down to the focal point instead of going through the lens. That's not really how we do the diagrams, so that the third ray is not right. So we've got A and D are good ones here. All right. Looking at number 16. Consider a diverging lens with a focal length of 5 centimeters and an object placed 7 centimeters to the left of it. All right, so we've got a diverging lens. I'm getting ahead of myself here, but diverging lens. And focal length is 5. 1, 2, 3, 4, 5. Remember, lenses have 2. 1, 2, 3, 4, 5. 2 focal points, but these are 5, each of them 5 centimeters away. In terms of, I guess we can do the object 7 centimeters. 1, 2, 3, 4, 5, 6, 7. So the object is over here somewhere. It's going to be DO. It says, where is the image? So let's go ahead and do a little math here. So we've got our lens equation. 1 over F is 1 over DO plus 1 over DI. And in this case, we're looking for DI. So DI, just rearranging this, is 1 over F minus 1 over DO. F, in this case, it's a diverging lens, so that means F is negative 5 centimeters. And this is telling us the object is 7 centimeters away from the lens, so that means DO is 7 centimeters. And so we're going to have 1 over negative 5 minus 1 over 7. Like negative 2.92. Since everything was centimeters, the answer is going to come out as centimeters, so that's DI. So that's the location of the image. And so for a lens, negative DI means when the light goes through, so which is the dark side? It means it's on the dark side. So which is the dark side? It's this. The light side is the side where after it hits the lens of the mirror, where does the light go? It keeps going on this one, so that's the light side. So the light side's over here. Dark side's over here. And so it means this object is over here. 2.92. Somewhere over here is where we expect the image to be. All right. Part B, use a straight edge to sketch a ray diagram on the diagram below. Use the dotted line position as the lens. Be sure to include, so I got DI, DO, and F in the lens shape already. Object, this is the object. And we need to get the image and the rays. Okay, so we have 3 rays that we draw. We do parallel focal. So we'll first go parallel here. Try to go straight, parallel, and then focal. So it's going this way, parallel is easy, and then it needs to be a diverging lens. So which focal point, the question is, is it going down here to this focal point, or does it go down here as if it came from this focal point? And so the answer is it's a diverging lens, so it's got to have that diverging pattern, so it needs to be going away from the middle line here. All right, so this would be ray 1, parallel focal. Okay, same kind of thing here for the second one, focal parallel. All right, so if we do we want to do like this? Do we want to go through, they all start at the image, start at the tip of the object. If we go like this, hit the lens and then go like parallel, will that be a diverging pattern? No, because look, if we go backwards, it's going parallel here and it comes to the focal point, so that's not right. All right, we want diverging. So let's look at going to this focal point. So we're going to draw the ray as if it's going towards this focal point on the other side. and then when it hits the lens, or the center of the lens, we're going to go parallel. Okay, and that does make the diverging pattern. If we look backwards, coming along parallel, diverges away from the center. So this is good for ray 2. And then ray 3 is everybody's favorite probably. Just starts at the tip of the object and goes through the center, continues on down. Alright, so ray 3 is there. Kind of hard to tell. So 2 is this one. Alright, so now we've got to figure out where is this image. Well, it's where it looks like these rays are coming from. And so we got to kind of do a dot, dot, dot back here. See where they all come together back here. And really 2 should tell us the answer, but the 3 verify it, and like that, it gets really close to where we said DI is supposed to be. I like it. So that is the image right in there. Okay. So that's good for part B. Part C, calculate the magnification of the lens of part. Of part A anyway. Calculate the magnification of the lens for this one above. So magnification is negative DI over DO. So it's negative DI, we have negative 2.92 centimeters, and then DO was 7 centimeters. Alright, so we get 2.92 divided by 7, and there's 0.417. Alright, so we expect the image to be upright since M is positive, and we expect it to be smaller than the object because M is less than 1 in magnitude, and that's what we see. Part D, a converging lens with focal length of 2 centimeters is placed 3 centimeters to the right of the first lens. Find the position of the image produced by both lenses together. Is it real or virtual? Okay, so we've got another lens, 3 centimeters to the right, so 1, 2, 3. So it's got an axis here, of course, where I have stuff written. And it's a converging lens, so it's going to be fat in the middle. Something like that. It's got a focal length of 2, so its focal length is on top of that one and here. So I'm going to call this F2, and I'm going to just write F2 here also. Okay, so find the position of the final image produced by both lenses together. So when we have 2 lenses, remember the DO for the second one, so DO2, or the object for the second one is the image from the first one. So this is going to be our object 2. So how far is it from the second lens? We've got 1, 2, 3. Well, we've got 2.92 plus the 3. So 2.92 plus the 3 centimeters that the lenses are separated. So it's going to be 5.92 centimeters for DO2. And we've got F2 is a focal length of 2, and it's converging, so it is just a positive 2 centimeters. So we can get our DI just like we had up here. DI is going to be 1 over F minus 1 over DO. 1 over 2 minus 1 over 5.92. Alright, so we get DI is 3.02 centimeters. Alright, and so that is positive, so it's on the light side, so it's on the side where the light goes after the lens. So we got 1, 2, 3, so it's basically right in here somewhere, 3.02. This would be DI2. Part E, add the second lens and its image to the figure. Be sure to include the focal point, all these things. Alright, so we've got this distance here is DO2, and we've got DI2 I just labeled. We've got F2, 2 F2s here. Alright, now we need to get the rays drawn. So the first ray, parallel focal. Let's see if I can find something a different color. So the first ray will be parallel focal, so it's kind of along this parallel from the other one. Parallel, and then focal. Something like that. And then focal parallel. So let's just kind of test out. If we go like this from the tip of the object through this focal point and then parallel, that will have the converging pattern, right? If we come backwards, parallel goes towards the center. So let's do that. Focal, parallel. And then the last one through the center. Okay, so we've got 1, 2, and 3 for here. And it's supposed to be right there. It's pretty close. Is that where we said DI2 was? Around 3. 1, 2, 3. Yeah. All right, so that's pretty close. I2 would be right there. Okay, 3 rays and lens shape. Yes. Okay, find the total magnification. So M total is M1 times M2. M1 is 0.417. M2 we haven't calculated yet, but it's going to be, M2 is going to be negative DI2 over DO2. So it's negative 3.02 over DO2 is 5.92. These are all centimeters, so that's good. Things cancel. So little M total is 0.417 times 3.02 divided by 5.92. .213, negative 0.213 for a total, M total. Okay. All right, let's go on to next page. Zoom in a little maybe. Okay, consider a convex mirror with a radius of curvature 10 centimeters and an image appearing at 4 centimeters behind the mirror. All right, so convex mirror, so convex radius of 10 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the radius would be way out the center of the circle that is the mirror. Would be roughly out here, so it's a pretty big circle. Not a whole lot of curvature probably. I don't know, just getting an idea here. Okay, and so radius of curvature R equals 10, so that means F is R over 2 plus or minus. Since it's a convex mirror, it means it's minus. And so in this case, F is equal to negative 5 centimeters. F. 1, 2, 3, 4, 5. So our focal point is there for our convex mirror. The image is 4 centimeters behind, so the image, so this would be our F. And our image position should be here. Hopefully it'll work out to be there. And it's asking for where is the object. And so again, same equation works for mirror. The mirror equation is the same as the lens equation. 1 over F is 1 over DO plus 1 over DI. So DO 1 over F minus 1 over DI in this case. So 1 over -5 minus 1 over 4. Okay, so we got 1 divided by -5 minus 1 divided by 4. -2.22 centimeters. DO. Why? That's not right. DO should not be a negative number. 4 centimeters behind the mirror, so it's on the dark side. So DI should be -4. So put a negative on there. Let's try this again. 1 divided by -5 minus 1 divided by -4. I think I did that wrong. -5 minus 1 divided by -4. 20. Alrighty. That's not good. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to have to change our scale here. So let's make this, each block be 2. So this DO is 20 centimeters. So this would be like R. Got ahead of myself. Probably be a bit more curved. No, it doesn't really matter too much. But then, so F is -5, so 2, 4, 5, so F would be here instead. And the image is at 4. So DI is here, F is here. Okay. So let's try this again. So this is our object at 20 centimeters. All right. And we need some rays. So first ray, number 1, parallel focal. Parallel. Then it looks like it comes from the focal, but it's got to bounce off of the mirror. We'll see how this works. I'm a little worried about this turning out, but we'll try. Alright, parallel focal, ray number 1. Ray number 2, focal parallel. So I'm going to try to go towards the focal point here. But then when it hits the mirror, gotta go off parallel. Come back parallel like that. Ray number 2. Ray number 3, center ray. So we kind of like to go down as much as that was going up, and it's got to come back and hit that and be symmetric. So I'm going to start here. Go down there, and then this one's going to come back to that same position except for down, something like that. This is ray number 3. Alright, now do they come together somewhere? Close to where the image is supposed to be. So let's get a dotted line going back, dotted line going back. Dotted line going back. Well, kinda looks like almost Right there is the image. Alright, so they look like they're coming from over here. Not too bad. Not too bad. Alright, part C. Calculate the magnification of the mirror. Same equation. M is negative di over do. Negative di is negative 4 and do is 20. So 0.2, 1/5. Yep. Negative and negative is positive. No units on magnification. 0.2 is M. If the object is 10 centimeters tall, how tall is the image? H by is magnification times HO. So 0.2 times 10 equals 2 centimeters equals HI. And so this is 10, that's 2. Yeah, I can kind of believe it. Does your ray diagram agree with your magnification calculation? And so magnification, so M is less than, magnitude of M is less than 1, and so it should be smaller. I should be smaller than O, yes, check. And M is positive, so it should be upright. And it is, check, yes. I guess yes, image is upright and smaller. That is good. Alright, 18. Consider a double slit setup with a 600 nanometer light and a screen 2.5 meters away from the slits. Alright, so double slit experiment. So for the double slits, what matters is the slit separation. Usually call that little d, but we don't have that. Well, that's what it says. Find the slit separation needed to make the second bright maxima 25 millimeters above the center. Okay, down here we're going to sketch the setup. So let's go ahead and sketch the setup. So we're going to have two slits, exaggerated here, but and then the screen. And we're going to have a maximum, and then some minima, more maximum, minimums. All right. So you want the second bright above center. So this is the first above center, second above center. All right. For the double slit, you got M equals 0, then M equals 1, and then M equals 2. All right. So this would be Y2. We got distance to the screen, 2.5. We got the slit separation here. Well, that's what we're looking for. Okay, and we're given that Y2 is 25 millimeters above center. Okay, find the slit separation. So for this we have for the bright maxima, so for maxima, constructive interference, we have the equation that well, d sine theta is m lambda for constructive whole wavelengths. But we don't want, so this would give theta, sine theta is m lambda over d, but we want the y equation. So we got y sub m, we just multiply that by L. Y sub m is like L tan theta, but then we use small angle approximations so that sine and tangent are about the same, so m lambda over d. L m lambda over d. In this case, m is 2, L is 2.5 meters, lambda is 600 nanometers. D is what we're looking for. So let's solve for D. D then is just going to be L m lambda over y sub m, y sub 2. M is 2. All right, 2.5 meters, 2 600 10 to the negative 9 meters divided by 25 times 10 to the negative 3 meters. So D is 2.5 times 2 times 600 times 10 to the negative 9 divided by 25 times 10 to the negative 3. 120 micrometers, 10 to the negative 6 meters. Okay, find the interference angle for the second order minima of this doublet. So now we've got second order minima. So this is for the minima for interference. We have minima, have the plus a half equation here. Do we have it on here? Maybe we don't have it on here. Nope. For the minima on the interference, so the interference is the double slit thing, then we have that d sine theta. This would be a good one to go ahead and write on your equation sheet. D sine theta is m plus or minus a half. That's not a half. M plus or minus a half of a wavelength. Remember, destructive interference. We want the wavelength shifted so that up and down, one is up while the other is down and vice versa, so they cancel each other out. And so we're going to go for, this is m, I guess second order, we just take second order to mean m equals 2. And so and we want the angle, so that's good. So we can just say sine theta equals m, we'll go up plus a half times lambda divided by d. And so theta is inverse sine of m plus a half lambda over d, inverse sine of 2.5 times lambda, which is 600 nanometers, divided by d, which we just got, 120 10 to the negative 6 meters. All right. Inverse sine of 2 plus a half times 600 negative 9 divided by 120 e to the negative 6. Not very big. 0.72 degrees is theta. Which, I mean, we use the small angle approximation. That's a pretty small angle, all right? Let me double check my numbers here. Yeah, 0.716 looks good. Okay, I guess we could call that theta 2, theta m here, theta 2. All right. Sketch the setup, including the interference pattern and the diffraction pattern. Oh, and the diffraction pattern. Yeah, that's kind of hard to do. All right, let's try drawing it. Okay, so this, the interference pattern, or like when in lab we saw the small dots with like this, and then we would have a space of darkness from the from each slit's diffraction. All right. So this is a very big setup compared to what we had in lab to get 25 millimeters for this. All right, because the second, so this is the 0, this is the 1, this is the 2 bright, so this would now be the Y2 25 millimeters kind of number. And then the second order dark, this would be 0 first, this would be the second order dark. Okay, and so this is the angle, theta 2 to the second order dark. Zero dark, 1 dark, 2 dark, yep. Something like that. So these are the light, the circles are the lights, and these are the darks. Okay, if the double slit is replaced by a single slit, find the second order minima dark fringe if the slit width is 1 micrometer. Okay, so for the dark pattern, or for the single slit, we can kind of think of it as just these blobs being all melded into one kind of a pattern. And for the double slit, for the diffraction, we really just have one equation that might be for everything. That might have been for the double, but really for the diffraction pattern, we just look at the minima. And so for that, again, we have D, not D. The diffraction pattern, we're looking at the slit width. We call that A. And so A sine theta equals m lambda. For this, it was really A over 2 sine theta equals m lambda over 2. The 2's cancel out, so we get this. And what are we asking for? Find the second order dark fringe. All right, so we're assume this is asking for Y2 again. Y2 dark. And so we want Y sub m equals m L L tangent theta, but again we're using the small angle approximation, so we got L m lambda over A for our Y sub m equation, and that's what we're looking for is the Y sub m, so we would plug everything else in. I think we got, so L is 2.5 meters, yes. M is 2 second order minima, lambda is still the same, 600 nanometers. And A is this 11, 10 to negative 6 meters. All right, so Y sub m equals what? Okay, big numbers, but anyway, 273 millimeters. So that was m equals 2. So I guess that kind of goes, if the little ones were 25 millimeters, the big ones were even bigger, but this is just going for a, it didn't say that the slit width, weren't given the slit width on the double slit, so we're not necessarily comparable. Okay, we'll just go with it. I think that, yeah, that agrees with what I calculated before. Find the angle for the first dark ring for a 11 micrometer round aperture now, not a slit anymore, but a round hole with the same setup as before. Find the angle. All right, so we have the equation for a round hole. We just have the angle equation for the first dark, 1.22 lambda over, I guess we call it D, where D is the diameter, or the width of the hole, diameter of hole, since it's now a round hole, which is that 11 micrometers. All right, so theta, find the angle, yes. Inverse sine of 1.22 times lambda, still 600 times 10 to the negative 9. And D is 11 times 10 to the negative 6. So this theta is, no, I didn't mean it. Inverse sine of 1.22 times 600 nanometers divided by 11 micro. 3.82 degrees. All right, 3 degrees. Looks good. All right, next page. Now on to the photoelectric effect kind of stuff. Consider photons hitting a sample of sodium metal with binding energy, work function, same thing, 2.24 eV. All right, what is the maximum possible speed of a released electron if the light has a wavelength of 400 nanometers? Okay, so the first question is, well, kind of the first question is, will there actually be any electrons? So let's go ahead and check to see if the energy of each photon, remember the photons are little packages of light that are going to be, each photon is trying to free one electron, and if the packets have energy above this binding energy of the electrons, then it can set them free. So let's go ahead and calculate E photon is, we're doing electron volts here, and so we have the one equation, 1,240 electron volts times nanometers over lambda, which is a nanometer, so that's good. So 1240 eV nanometers over 400 nanometers. So the nanometers are going to cancel out. We're going to get EV, so we got 1240 divided by 400. And remember, this is just H times C in units of nanometers, because E is HF, but F is C over V, so or C over lambda, so it's HC over lambda is also E. So that's just where this equation comes from. All right. So we get 3.1. EV is energy of one photon at this 400 nanometer, which wasn't what they asked for, but it is bigger than the binding energy, so we will actually get some set free. So that's good. All right, so the equation is E of the photon equals the work function plus the kinetic energy the maximum kinetic energy we can get for the weakest bound electron. So take the least amount of energy to get it out of the atom, so we'll have the most energy left over to go fast. All right, so we want the maximum speed, so we want the maximum KE, so let's solve for KE max is going to be, of course, E photon minus the work function, or the binding energy, which is 3.1 EV minus 2.24 EV. So KE max is 3.1 minus 2.24. 0.86 EV, which is not too helpful when we're trying to find speed, because we're going to try to use KE equals 1/2 mv squared, and we need this to be energy to be in joules to get velocity in the right units, and so let's change this to joules. So 1 electron volt is 1.602 10 to the negative 19 joules. So, yep, so got that number times. We have 130, we'll go 137.8 to keep a little extra sig fig just for now. 10 to negative 21 joules. All right, so that equals 1/2 m. So just plugging this in here. 1/2 m. We're talking about electrons here, so mass of an electron 911 10 to the negative 31 kilograms v squared, and so that gives us V must be square root, solving this, dividing through 137.8 times 10 to the negative 21 divided by 1/2 times 9.11 times 10 to the negative 31. Alrighty. Okay, let's see if we can calculate that. Square root 137.8 10 to the negative 21 divided by 0.5 times 9.11 e negative 31. Looks pretty good. Okay, so we get 550 times 10 to the third meters per second for our V max. Okay. Yes, this is not what I got before. Let me check. Yes, good. All right, what is the minimum frequency of light that can cause electrons to be emitted from the sodium? Okay, so the minimum frequency would be when E photon equals work function, and then the kinetic energy, we're just going to assume that there's no extra energy. So it'll just get out and it won't have any energy to go anywhere, but that will be the minimum frequency. And remember, another equation for E of the photon is HF. So we're going to say HF equals binding energy, which is 2.24 EV. We didn't convert that to joules, which we will want to because this H is in joules seconds, and so I multiply this by fraction 1 eV on the bottom, 1.602 times 10 to the negative 19 joules on the top. (358.8 10 to the negative 21 joules), and that equals HF, so F equals that 358.8 times 10 to the negative 21 joules divided by H, which is 6.626 times 10 to the negative 34 joules times seconds. So the joules cancel, we end up with 1 over seconds, which is what Hertz is, so that's good. 358.8 10 to the negative 21 divided by 6.626 e negative 34, 542 10 to the 12th Hertz. That is the minimum frequency. Doesn't sound very minimum, sounds pretty big, but it's the smallest frequency of light, or smallest frequency of an EM wave that will free a photon with this, that will free an electron with this binding energy in sodium. Okay, what is the maximum wavelength? Okay, so very close to the same question. Minimum frequency gives a maximum wavelength, they're directly related just by the wave function. So we've got, just going back to the basic wave function, lambda times f equals c. So we want, in this case, lambda max will be c divided by f min. Right, divided by the smallest thing makes the biggest thing over here, so it's going to be 3.3 times 10 to the 8th meters per second divided by 542 times 10 to the 12th Hertz, which is 1 over seconds. So those 1 over seconds cancel. We end up with meters, which is what lambda should be, so that's good. Lambda max 3 times 10 to the 8th divided by 542 10 to the, oops, not negative, 10 to the 12th. 554 10 to the negative 9 meters. 554 nanometers. That's good. Okay. D. If a half a milliwatt laser is used to shine 400 nanometer light on the sample, how many electrons are released per second? So 400 nanometers, that's what we're talking about up here again at the beginning, not this maximum. How many electrons per second? So this is watts or milliwatts power, which is joules per second. So we have 0.5 times 10 to the negative 3 joules per second is our flow of energy. And we want to know how many electrons per second. So we're going to divide this by how many joules per electron. Joules per each electron, how much energy it takes to free each electron. So that's how much each photon. So remember, it's a one-to-one kind of thing. One photon releases one electron. So the photon energy, we still didn't calculate that, did we? Photon energy for the 400. Oh, yeah, no. Oh, yes. No. We have it here in electron volts, but we want it in joules. I think I haven't calculated that yet. So, so we want well, we'll just take it here. So we have E photon is equal to 3.1 electron volts. That was for the 400. Yep, just double checking. And we want that in joules. So 1 electron volt, 1.602, 10 to the negative 19 joules. So in joules, you have 3.1 times 1.602 negative 19. 496.6 times 10 to the negative 21 joules. All right, so that's how much each photon's energy is. And each photon does 1 electron, so that's joules per electron. So we put that in here. 496.6 10 to the negative 21 joules per electron. So divide that out. 0.5 times 10 to the negative 3 divided by 496.6 10 to the negative 21. 1.01 times 10 to the 15. Joules cancel. That shouldn't be joules times seconds, should be joules per second. The joules cancel, and we've got electrons on the bottom of the fraction, so like when we flip over and multiply, it becomes electrons per second. Yes. Alright, so that's how many electrons are released per second. A whole bunch. 1.01 times 10 to the 15th electrons per second. Alright, part E. What is the maximum kinetic energy of a released electron if the light has a wavelength of 500 nanometers? Alright, so is this, we are still getting some. It's underneath the maximum, so that's good. So maximum KE is just kind of going back to this equation again. So we have E photon is binding energy or work function plus KE max. And so KE max is energy of the photon minus binding energy, work function, and energy of the photon. We'll do this all in electron volts, so we'll do the 1240 eV nanometers divided by lambda minus the binding energy, which is I guess I might as well put in lambda. 500 nanometers minus a 2.24 electron volts. So KE max equals 1240 divided by 500. Since the units are nanometers, we don't have to do the -9 stuff. We'll end up with EV there, and then subtract 2.24. We get 0.24 electron volts. It doesn't say what units it needs to be in, so we'll just call electron volts good units. It's a kind of energy unit, so that's good. So that should do it for sample test 5.